Let us move on to the first introduction of the Nastran and Patran software. Under this, we will be studying the virtual project development, a first look at Patran, profile of a simulation project. Virtual project development is an approach that makes a design by the earliest concept stage and completely evaluates with design specifications later. Uses this information to guide the development processes. It enables companies to leverage resources by optimizing project design, leading to improved performance, reduces the need for real-world prototype, verifiable quality improvements, minimized operational problems and failures. This process is the capability to use the simulation software to represent physical environment and events in evaluating the operability of a project design. Simulation begins with building a model of a project structure and generating a simulation of its operating environment. Then, using specialized simulation software called finite element analysis codes, the simulation model is analyzed to determine how it responds to the imposed environment. This response is then measured against allowable limits, test data, and knowledge database. It is the product design data detailing dimensions, geometry, parts, and assemblies generated from a computer-aided design (CAD) process that are building blocks for a simulation model. The five key features form the foundation for Patran, and a unique infrastructure linking these features gives Patran power and versatility. Stimulation task interference. The task interference is what you see on the screen when you use Patran. The interference includes menus and toolbars for using tools and applications, forms for inputting data, icons for showing the status of operation, and viewports for rendering computer models. The interference provides access to all the functions and capabilities of Patran. Tools and application. The tools and application are the mainstay of Patran. Tools help you carry out tasks inside Patran. There are literally hundreds of tools that help you create product simulation, set up analysis, and compile the analysis result. Many of the tools automate repetitive tasks and could take hundreds of hours if performed manually. Other tools are in place to check for error or to signal you in case of inconsistency. Application modules. Application modules perform larger, more specialized tasks, often outside Patran. You use application module to conduct a finite element analysis. Together, the tools and applications help you carry out the simulation project. Project database. An important feature of a Patran infrastructure is the integrated database system. All of the information about your model and any analysis are stored here. This means you always have a complete history of your simulation project and a convenient means to partitioning the model into parts, comparing models, studying design changes, and evaluating compound effects of an environment. Open architecture. Another important attribute of Patran is its open architecture. With open data exchange, you can share information with a variety of sources and software programs, including leading CAD systems, FAE codes, specialized modeling and graphics program, and material and product knowledge database. Using different software programs for different phases of a simulation process adds versatility. It also increases productivity since data and model created by one program can simply be brought into Patran with little or no time wasted in data conversion. Profile of a simulation project. Simulating a product design. This stage is typically the most time intensive. The simulation or model must describe the shape and size of the product, detail what materials are used to construct the product, stipulate how the product is assembled, and define the environmental forces that the product endures. The majority of the tools in Patran help you construct this product design model. Turning product into geometric models. Patran provides its own set of goals for geometry creation and editing. Using these tools, you can quickly create parts with 2 or 3-dimensional wireframe, surface, and solid geometry. The geometry application form provides over 100 options for creating basic geometry objects as well as numerous editing and verification functions. Meshing and creating elements. Once you have imported or created a geometry, you can create and verify the finite element mesh using a powerful suite of meshing tools. These tools include industry-leading auto meshers for curves, surfaces, and solids, as well as mapped meshing and paved surface meshing. Additionally, you can edit the analysis model interactively. Modeling material. The materials application is where you define the materials for your analysis model. A material model is a group of material properties that describe what your model is made up of, such as steel or a composite, and the attributes of that material, like stiffness, density, and so on. Once you define the material for your model, you will assign them to model regions. Simulating forces and loads. The finite element analysis tests a particular model reaction to particular loads and constraints imposed as boundary conditions. Loads are environmental factors such as force, pressure, temperature, and voltage. Boundary conditions are described in terms of degrees of freedom and are the directions in which the edges of the model are free to move in 3D spaces along the translational, that is straight line, or a rotational path. Analyzing model with environmental loads. Once you have completed the product design model, the analysis stage of the simulation project begins. There are several options for running a finite element analysis using Patran. Selecting an analysis code. You initially select an analysis code when you begin each simulation project. Patran assumes that you are using a single analysis code as you build the product design model. Patran stores the information using the formats and naming the analysis code. When you change the code selection, Patran attempts to convert all of the data into a new format. Tailoring the model for a selecting analysis code. You will need to define element types such as beam, shell, and so on, and element related properties for the region of your model. Then assign these definitions to geometric or FEM entities. Element type selection is based on the model's behavior. Additional properties describe attributes such as thickness of a plate, the spring constant for a spring, and an area for a bar element, materials, and so on. Running finite element analysis. The analysis application provides the link between the Patran environment and the analysis solvers. These solvers can include MSc analysis codes or commercially available solvers or property codes developed by analysts for their own exclusive use. The analysis application provides the means to identify a desired analysis type, define translation and solution parameters, select a sequence of load cases, select desired output, send the model data to the analysis solver, read result quantities from the result files. Compiling the analysis result. Finite element results generated in the second stage of the project generally take the form of numbers, such as the amount of displacement at a point in the model. However, it is difficult to gain a real understanding of how a model behaves by looking at the stack of numbers on paper. The third stage of the simulation project entails using Patran, ability to visualize results using computer graphics, animation, and other result tools. Visualizing the analysis results. Patran is state-of-art in its ability to display sort, combine, scale, and query in a general way is a single result database. After execution, analysis results are loaded directly into the Patran regional database and can be sorted by time step, frequency, temperature, or spatial location. Sequence of tasks. A standard simulation project carried out from start to finish would typically follow the sequence of tasks outlined above. However, it is important to point out that this task sequence is a generalization. In reality, each simulation project is unique with a distinct set of requirements, resources, data, and assumptions. These factors dictate both the task and the sequence. Within the simulation process, there is an inherent feedback loop. Results or problems encountered in one stage of the project may prompt you to go back and change or re-examine a previous stage. Analysis results that exceed requirement often drive model and design changes. Within each stage, the sequence in which you perform the task may change. For example, you may choose to model the material in your model once the geometry is complete, or you may elect to wait until after the meshing is done. This depends on whether you plan to define the materials accordingly geometric region or an element by element basis. As you learn to use Patran, keep in mind that the task sequence are flexible to certain degrees. For each project that you begin, you will have to evaluate requirement, resources and data to develop the task separately. Let us move on to fundamentals in the next course.